Okay, sorry guys, got cut off there. So in example 3, we have a bicycle tire with a mass of 3 kilograms. Okay, the tire has 4 spokes with a mass of 1 kilogram. Okay, and the length of each spoke is 0.33 meters. If the system is rotating at 30 radians per second, we need to determine the angular momentum and the rotational kinetic energy. Okay, first up here, we know that we typically model a wheel as a hoop. So you can say that this outer radius here, this mass, you can model as a hoop. And then we have 4 spokes, which look most like rods. So we're going to model these spokes as rods and the hoop, the wheel as a hoop. Show that for the moment of inertia of the rod, about the center of mass is 1/12 ml squared. Note that the axis of rotation is directly in the center of each rod and directly in the center of the hoop. So we can use those shortcut equations without having to derive them with calculus. Okay, so we know that hoop we model as mr squared, just like a point mass. To find the total value of I for this system, we have to add the individual components. So I total is going to be 4 times the moment of inertia of a rod about the center of mass, plus the moment of inertia of a hoop about its center. Again, we know that there is no external force added to the system. Okay, to find angular momentum, we're going to determine L. Okay, so we know that angular momentum is the moment of inertia times the angular velocity, just like linear momentum, right? The rotational equivalent of mass is inertia. The rotational equivalent of velocity is angular velocity. So we're going to substitute in I total for I. Okay, technically, we have 4 times a 12, we get 4/12, times the mass of each individual rod, which is 1 kilogram, times the length, that should be an L of here. The length of each rod is 0.33 meters squared. We're going to add that to the moment for a hoop. The mass of the hoop is 3 kilograms. The radius of the hoop would be half the length of the spoke or the rod, which is 0.165 meters. Don't forget to square it. Okay, the whole system is rotating at omega. So you multiply that total value for I by 30 radians per second. Simplifying, we get 0.1179 kilogram meter squared times 30 radians per second. So the angular momentum of our bicycle tire is 3.54 kilogram meters squared per second. Remember that the units for angular momentum have 1 additional meter compared to linear momentum due to the moment of inertia. Okay, and L is positive. That means that the tire is rotating counterclockwise. Okay, so finding I first. If we have a system with multiple parts, we must find total I before we can find the momentum. Okay, so now that we've found the angular momentum, we need to find the rotational kinetic energy. We know that rotational kinetic energy is 1/2 omega squared times I. Okay, so we're going to plug in for I total and omega, which was given to us in the problem. So for part B, we have EK rotational is 1/2 I times omega squared. So you plug in for our expression for I total. So 4 times the 12, we get 4/12. times 1 kilogram times 0.33 meters squared, plus mass of the hoop, which is 2 kilograms, times the radius squared, 0.165 meters squared. Okay, that simplifies to 0.1179 kilogram meters squared. Okay, we square 30 radians per second, multiply by I, and then by half. We find that the rotational kinetic energy of the system is 53.08 joules. Okay, so omega here is positive because it's rotating counterclockwise. And even if omega is negative, right, when you square a negative value, you get a positive value. So rotational kinetic energy will not be negative. Okay, energy cannot be negative. All right, let's take a look at a parallel axis theorem example. Okay, so in example 4, we have a 20-gram bullet traveling at 400 meters per second. Okay, the bullet strikes a 20-kilogram, 1-meter wide door at the edge opposite the hinge. Okay, so the bullet is going to hit on the opposite end of the door compared to the axis rotation. The bullet embeds itself in the door, causing the door to swing. What is the angular velocity of the door just after impact? Okay, so here we have an inelastic collision as the bullet embeds itself in the door. Okay, so that means that the bullet and the door will move together with the same angular velocity after the collision. Because we're looking at a system, right, and technically the force of the bullet on the door is the same as the force of the door on the bullet, that force is internal to the system. If there is no external force acting on the system, the angular momentum is conserved. Okay, so we're going to use conservation of angular momentum to find the final angular velocity of the door after impact. We're going to model the bullet as a point mass. Right, the moment of inertia of a point mass is mr squared. And we will model the door based on the diagram that's given to us. Okay, we're going to assume that it takes the shape of a rod. So we're going to use 1/12 ml squared. But if you notice here, let's take a look at this rod. So taking a closer look at this rod, right, technically the center of mass of a rod is at its center. Okay, so it'd be halfway in between the two ends. Technically, the rod, aka the door in this situation, is going to rotate about the end. The axis of rotation is parallel to the axis of rotation about the center of mass. Right, so objects, if not fixed to a pivot, would naturally rotate about an axis through their center of mass. Okay, so we could use the integral, okay, of r squared dm, find an expression for dm, and integrate across that area. Okay, or technically here our linear mass density, or because the actual axis of rotation is parallel to the axis about the center of mass, we can use the parallel axis theorem. Okay. Just a reminder review, parallel axis theorem states that if the axis of rotation is parallel to the axis about the center of mass, we can find the moment of inertia about that axis by taking the moment of inertia about the center of mass and adding the total mass of the system plus the distance from those two parallel axes. So to find the moment of inertia of the rod about that axis rotation, or that point P, we have to take I at the center of mass, which would be 1/12 ml squared, plus m times d squared. Okay, L here is the length of the whole rod, which is 1 meter. D, the distance between those two parallel axes, is 0.5 meters. So we're going to plug in. So we have 1/12 times 20 kilograms times the length of the rod, which is 1 meter. Don't forget to square it. Plus mass, which is again 20 kilograms, times the distance between the axes, which is 0.5 meters, squared. So we find that the moment of inertia of the rod about that hinge would be 6.667 kilogram meters squared. Okay, so if the object does not rotate about its center of mass, we have to find the moment of inertia either using the integral form of I, okay, which is r squared, integral of r squared dm, or if the axes are parallel, we can use parallel axis theorem, which saves us a bit of time. Okay, so now that we have the moment of inertia for the rod, aka the door, we know we're modeling the bullet as a point mass, okay, with moment mr squared. We can use conservation of angular momentum now that we have our expressions for I. Okay, so initially, only the bullet has angular momentum. Okay, the door is technically stationary. The door is not rotating. So although we have our value for I, omega for the rod is going to be 0. So it's going to simplify to 0. After the collision, the bullet and the door have the same final angular velocity. So omega sub rod final and omega sub bullet final are equivalent to each other, so we're going to substitute in omega final. Okay, we're going to distribute that as the expression. We have I rod plus I bullet times omega final. And that looks almost identical to our inelastic equation for linear conservation of momentum. Okay, so let's plug in what we know. So we know the door initially has no angular momentum. The bullet, however, has angular momentum. I for a bullet is mr squared. We don't know omega of the bullet, but we do know its tangential velocity. So we're going to substitute in v over r for omega. You'll notice on the left-hand side here that one of our r's will cancel. Okay, we determined I of the rod to be, from our previous step, 6.667 kilogram meters squared. Okay, we must add the moment of inertia for the bullet times the final angular velocity. Okay, so let's think about R here. So we know that the bullet is moving towards the door. Technically, the bullet is going to rotate about this axis of rotation once the bullet and the door collide inelastically. So R must be the distance from the point particle to the axis of rotation. The distance from the point particle to the axis of rotation is the length of the door because it hits on the outer edge of the door. So R here for a point particle needs to be L, okay, which is 1 meter. So one of those R's will cancel. We'll plug in for the mass of the bullet, the radius of the bullet from the axis of rotation, and then the tangential velocity of the bullet. So you have 0.02 kilograms times 1 meter times 400 meters per second, which is equal to the combined moment of inertia of the system times omega final. So simplifying, we get 8 kilogram meters squared per second equals 6.687 kilogram meters squared. We divide both sides by 6.68. We find omega. Okay, the kilograms cancel, meters squared cancel. We're left with blank over second. Right, omega must be measured in radians per second. So omega final is 1.196 radians per second. The final angular velocity of the bullet door system. Okay. So in Google Classroom, you're going to fill out the Google Form for today. Okay, the problem is very similar to one that we just took a look at. But in the problem posted in the forum, you'll notice that the bullet actually hits at the position of the center of mass. Okay, so your value for I total is going to change slightly due to the radius from the point particle to the axis rotation, altering slightly there. All right, so if you have any questions, you know what to do. Send me an email or join the Google Hangout. Have a good rest of your day, and I will talk to you tomorrow.